Good day, physics class. I was just messing with you. Made you think that your computer is frozen. So I hope everybody enjoyed their spring break. I'm hoping everybody is staying healthy. Remember, wash your hands, wash your hands, wash your hands. Don't see other people. Yeah, okay. Okay, so we've got some stuff to get through here. So there was an assignment from before break, which will be due this Friday. Okay, so assignments can be due on Fridays, unless we have a quiz. So last week, or 2 weeks ago, we had a quiz, and we'll have another quiz this week. But you need to make sure that you're keeping up, and if we have a quiz, you need to make sure you get that done. So there was an assignment from last Friday. I'll put that back up again in Moodle for this week so you can see that as well. There will be an assignment for tonight too. It's answering some questions. We'll get there in a minute. So this is chapter 13. This is liquids. Oh, by the way, the test, stay tuned. There'll be more information on tests from chapter 12. We'll get to that. Don't worry, okay? So chapter 13, this is about liquids. These are the things we're going to cover throughout this chapter: pressure, liquids, buoyancy. Why do things float? Okay. Pascal's principle. It's a big deal. Okay. All right. So first of all, which one has the greater pressure? Is it the large but shallow lake? If you go down to the bottom, is that going to be more pressure because it's bigger? Or the small but deep pond, is that going to give you more pressure? It's smaller. See, it's very small. This one's very big. 3 meters deep, 6 meters deep. Where are you going to get the deeper pressure, the more pressure when you go down to the bottom? Or which fish, let me get this out of the way. There we go. Which fish has the greater pressure? Okay, so obviously this one, with this fish, it's shaped that way. The water's all pushing down on top of it. This one, it's shaped differently, so as the water goes down. What if the fish were over in this one? What if the fish were over here? Hey, what if the fish were swimming along the bottom here? Where would the fish have the greater pressure? Well, let's, I'm going to shrink myself a little bit here. There we go. All right. Okay. So pressure is the force per unit area that one object exerts on another one. If we looked at it in an equation, we'd say P equals F over A. Force over area. Pressure equals force over area. So the pressure depends on the area, obviously, and the force which is pushing down it. Now imagine that you took your finger, actually just take the palm of your hand and push on your arm. Take your finger, push with the same amount of force. Take a pencil or a pin and push with the same. Now, which one's going to have the greater pressure? Well, obviously that pin is going to hurt like the dickens, right? Why? Well, the area at the end of the pin is very, very small. The area at the end of the heel of my hand, this is much bigger. So when I push with the same amount of pressure or same amount of force, this has a lot bigger area, a lot smaller pressure. So it depends on the area which the force is distributed. So the units, Newton per meter squared, of course, force is in newtons and area is in meters squared, or we could say pascals. So imagine that I'm laying on a bed of nails. Why doesn't that hurt me? I put in Moodle a video of Ellen DeGeneres lying on a bed of nails. So when you have a second sometime, watch that video of Ellen DeGeneres laying on 256 nails or something along that. I don't remember the exact number. Why doesn't this person get hurt when they lay on a bed of nails? Okay. At the beginning of the video with Ellen DeGeneres, they throw an apple down on it, and the apple sticks right in the nails. But when you lay on them, it doesn't hurt. Why? Well, the combined surface area of the nails is tolerable. So, so it's the same amount of force, but the area is very big because there's a lot of nails. So there's a lot of nails. If you laid on one nail, man, it's going to hurt. If you laid on 10 nails, it's still going to hurt. But when I'm laying on 256 nails or 1,000 nails or whatever it is, my force is divided between all of the nails. It doesn't hurt. It doesn't even hurt my skin. All right, so when you stand on 1 foot instead of 2, tell me about the force I'm exerting on the floor. Less, same, more, none of the above? The force now, okay? Not the pressure, the force. Well, the force is the same because push down 1 foot, push down 2 feet, the force is still the same, okay? But what about the pressure? E equals F over A. Force is the same. Area is smaller. So then the pressure I exert on the floor must be more. That's right. So twice as much because I'm only standing on 1 foot instead of 2. So in a liquid, the force per unit area, pressure in a liquid, this is the force per unit area that a liquid exerts on an object. So this is completely dependent on the depth, not the volume. Remember going back to the beginning, and we said, okay, big lake, small pond, you know, you go down the bottom, where's the more pressure? Or the fish. Okay, so this fish at one of the beginning slides. Which one has a greater pressure? Well, all it matters is how deep you are. Try this. Go down to the bottom of your pool in the shallow end. Okay, doesn't really hurt that much on your ears, right? Go down the bottom of the pool in the deep end. Ooh, that hurts a little bit more. What if you went down bottom of your pool and you had a deep pool? What if you went snorkeling or scuba diving and you go down to the bottom? Okay, the deeper you go, the more weight of water there is above you, the more pressure there is. So some of you that have gone scuba diving or snorkeling, you know this, okay? And you know the deeper you go, man, that really hurts your ears. And you can equalize your pressure underwater, but it hurts until you equalize your pressure. So the pressure acts equally in all directions. It doesn't matter, if I go into water, it doesn't matter how I hold my head, doesn't matter if I'm looking up, looking down, looking around, whatever. The amount of pressure is the same on my ears, no matter how I hold my head. The bottom of a boat, a cruise ship, an aircraft carrier. The bottom of a boat is pushed upward by water pressure. We don't usually think about that, do we? The force of the water pushing up on the boat. Yeah, there's pressure, there's a force pushing up on that boat, okay? Also, if you take take a beach ball and you push that beach ball under the water, what happens when you let go? The beach ball flies up out of the water, right? Why? Well, it's because the pressure of the water, the force of the water is pushing it up. It doesn't matter the size or shape of the container. The pressure of the liquid is completely dependent on the depth, okay? So this lady here, she has several different shapes and sizes of the container and the fluid, but whatever the shape of the container, the pressure at any depth is the same. So liquid pressure is weight density. Okay, we talked about density before, D equals M over V. We're talking about weight density. Now we're talking about the force of gravity times the density times the depth. How does that work with salt water, fresh water? Liquid pressure, weight density times depth. Is salt water more dense or less dense than fresh water? We'll think about that. So anyway, water pressure provided by a water tower is greater if the tower is, where's the water pressure going to be greater? If this is higher, if this holds more water, or both? Well, obviously, if it's taller. It doesn't matter how much water is in there. All that matters is how tall is the water tower. The taller the water tower, the more water pressure there is. That's why they built these water towers really high, so that the water pressure can be distributed over a great distance and still have very, very high water pressure. So the effects of water pressure acts perpendicular to the surfaces of a container. So it acts at a right angle. So if I take a cup, I poke holes in it, the water pressure is at a right angle, at a right angle, at a right angle. Okay, so liquid squirts out, straight out, but then guess what happens? Gravity starts working on it as well. So there's a force going out, but there's also an acceleration coming down. Okay, the greater the depth, the greater the exiting speed. So down here, we'll see this is going to squirt out farther, faster. Why? Because there's more pressure pushing down on this cup, which causes the water to squirt out farther. Okay, here's the assignment for tonight. Page 259, questions 1 through 6. Don't email them to me, no. Go to Moodle, find the assignment, write out your answers, and then you're going to upload the assignment into Moodle and submit it that way. Okay, I think that's all we have for today. Oh, one other thing before I forget, don't forget to do the daily forum. Okay, every day we have to do daily forum. That's your way of checking with me, saying, hey, I'm here. Okay. And of course, if you have any questions, you're always free to contact me. So, until tomorrow, wash your hands. Oops, I'm still here. Keep washing. 20 seconds. 20 seconds.